Okay, welcome to this video. This is Foundational Mathematics Lesson 2. And so today we're going to be discussing where we left off last time. Maybe if this is going to work. Sorry, my pen stopped working. Okay, so we're going to be discussing, oops, I don't want to move myself, go back. The conditional statement, and then the statements that are related to the conditional statement in that they are sort of reconfigurations. Okay, so remember what a conditional statement is. It's we have two mathematical statements, P and Q. The conditional statement is P then Q. So let P and Q be mathematical statements with a truth value. Of course, that's the nature of a mathematical statement. So P implies Q. That's one way we can interpret this. P implies Q. Or we might say if P, then Q, like this. Okay, so in this case, the P is our hypothesis and the Q is our conclusion. Okay, so with this statement, we have some statements related to it. And essentially, these are just reconfigurations of this statement. So the first one is called the inverse. Actually, I want to do the converse first. The first type is called the converse, and this is one that is, it's a little subtle it's a little subtle. It can be subtle because it's not logically equivalent to the conditional statement P then Q, although oftentimes it's mistaken that way. So the converse is rearrange the order, not R, to have Q then P. Okay, so this is our converse. We also have something called the inverse. And the inverse is negating P and then also negating Q. Okay, so the inverse would say not P, then not Q. And then the last one, which is probably one of the more useful in terms of proving mathematical statements, is called the contrapositive, which we would write as not Q implies not P. Okay, now these two, and I'm going to prove it here in a moment, these two are logically equivalent. And by extension of that also means that these two are, wait a minute, sorry. Yeah, that's right. These two are logically equivalent because actually the inverse would be considered the contrapositive of the converse. Okay, so now what I'm going to do is I'm going to make a truth table to show that the original conditional statement and the contrapositive are logically equivalent as are the converse and the inverse. Okay, so let's see. Well, let me see if I can do this the easy way. Here we go. So I'm just going to grab a truth table here if I can. Maybe. Let's see if it works. I don't know. Usually I draw it, but it just takes so long to draw one. So, okay, here we go. So yeah, this should be good. Not sure how many of these we'll use, but we'll start by writing P and Q. And hold on, my Q is not very Q-like. Actually, I want to move it over. Okay, so I'm going to put the P and Q here. And then I'll have my P implies Q. Now you can make these even more detailed than this, but I think I'm just going to just stop at a certain level here. So first I'll have my conditional, then I'm going to use the converse next. So I'll put the converse here. And then how about here, we'll put the inverse, which is going to be not P, implies not Q. And then lastly over here, we've got our contrapositive. So not Q implies not P. Okay, so we have our statements here. So let's just go through. We're going to have true, 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 false, false, true, and false, false. All right, so we know already the truth values for the if-then statement. We did that in the previous video. So this one is true every case except in the case where the premise is true, but the conclusion is false. So that's the only time it's false. So I'm going to write down a red F there. Well, I don't want to do that actually. Let's just keep using the same color. Okay, so it's going to be true, false, true, and true. Okay, now for Q then P, it's going to be, we have to look at this column first and start from here and go in the direction to the left. So the first one is true. Second one, false implies true, that's true. Third one, true implies false, that one's false. And then the last one is true. Okay, so that's our converse. Now let's look at the inverse, which according to what I said, the converse and the inverse are logically equivalent. So we should get exactly the same truth values here at exactly the same times. So the first one is, so it might be helpful to do like this. Let's see, I'll just write, since I have these here, I'll make a not P and a not Q. Why not? Okay, so then, hold on, let me make it a little bit neater. So I've got a not P and a not Q. So here, if P is true, then, so basically what's going to happen, we're going to reverse all of the truth values, right? Because the negation is doing that. And this one's true, true. Okay, so I think that's correct. Yeah. Okay, so now I'm just going to use those two columns. So not P implies not Q. Both are false here. So that means this is true. And then I have false implies true, also true. True implies false, that's false. And then true and true is true. Okay, so as we mentioned, you can see here that these two are the same. The truth values are the same at the same time, which means these are logically equivalent. And now the last one, when I go do the contrapositive, you will see that this will be exactly the same here. Okay, but again, we're going to look at Q implies not P. So the first one, not Q, is false, P is false. That means this is true. The second one, not Q, is true, and not P is false. So that means this one is false. And then every other time it's true because it's still a conditional statement, right? So as you can see, the contrapositive and the conditional statement are, in fact, logically equivalent. And so I could write it down like this. So I would write P implies Q is logically equivalent to not Q implies not P. Not Q implies not P. Okay, and let me give you an example using words. Okay, so let's do that. So here's my statement. My statement is, if two angles are linear pair, I should say are a linear pair. If two angles are a linear pair, then they are supplemental. Now, is that true or false? Yes, definitely is true. Just a reminder about that. So a linear pair are two angles that share a line. So for example, here, let's say I've got this straight line. We'll call it L. And then I have an angle here, which I'm going to call alpha. And then this angle here called theta. So given that L is a straight line, it's always the case that theta and alpha are a linear pair. They're a linear pair because they are adjacent to each other on a straight line. So they're next to each other on a straight line. And the angle that is created by taking, so for example, this is a line here. If I take and move it all the way over, open to here, that's half of a circle, that's 180 degrees. And so this linear pair, the sum of the linear pair will always be 180 degrees. Okay, so it is in fact true that they are supplementary. Oops, I forgot to write. Now, supplemental is okay. So supplementary means supplementary angles. These are angles whose sum is 180 degrees. Okay, so all right, so now let's look at, well, first we're going to just write down some of the other variations. Okay, so if P, then Q is true, certainly. So, so our statement P is like this one. So P is the statement that the two angles are a linear pair, and then Q is the statement that they are supplemental. So P implies Q is only false if you have a linear pair, and then they're not supplemental. So if you could say two angles are a linear pair, then they are not supplemental. Well, that's false, right? Okay, now let's look at the converse. So we know the converse is going to be Q implies P. So in this case, how do we state the converse? It would say that if, hold on, I want to use that color. Let me use a different color though for the converse. How about orange? Okay, so if two angles, I'm going to use an abbreviation for angles here. If two angles are supplemental or supplementary, I can use both, okay? If the sum of the two angles is 180 degrees, then they are a linear pair. Now, is this true or false? Okay, so this statement was true, right? This statement, on the other hand, is false. Why is it false? So that, before I move on to tell you why it's false, let me explain what does this tell us about the conditional statement and the converse. So P implies Q is not logically equivalent to Q implies P. Okay, so it's not the case that these are logically equivalent, because here you see an example, right? But maybe you're not convinced. So remember what I said, it means for lines to be, not lines, for angles to be supplemental. So suppose I've got two parallel lines, okay? So I've got a parallel line L and M. So L, I'll say L is parallel to M. And then suppose I've got a third line passing through here. Okay. And let's put some arrows here to make them very line-like. We'll call this Q. So Q is a transversal through two parallel lines. Now, if we consider this angle here, I'll call it 1 and 2. What do we know about angle 1 and 2? Well, L is a line, so angle 1 plus angle 2, these are linear pairs, so they are in fact supplementary, so they do add up to 180 degrees. Now, the other thing about parallel lines cut by transversal is that their corresponding angles are congruent. So I'll just call this angle 3. Now, angle 3 is corresponding angle with angle 1, which means that they are congruent. Okay, so, and in fact, that's one of the definitions of parallel lines. In fact, this is an idea, well, I don't want to get into it because I've got another example, but the conditional statement is if two lines are parallel, then their corresponding angles are congruent. And actually, in this case, in the case of parallel lines and corresponding angles being congruent, this statement, the converse is also true. Okay, so, but I'm giving you an example now where the converse is not true. Okay, but let me continue. So angle 1 is congruent to angle 3, which means that what? It means that angle 3 plus angle 2 will add up to 180 degrees. So in other words, angle 3 and angle 2 are supplementary, but they're not a linear pair. Okay, so this is a good example of how we disprove things in mathematics. Disproving things, well, I don't want to say it's easy because when you're learning it, you have nice examples. Maybe you have like softballs. People say, you know, you have a softball, meaning you have a question that's just designed to show you the explanation. And you get harder questions. Some books, I've seen some books that have like 30, 40 questions per section. And if you were even if you were like the best student, how could you conceivably try to do all these very involved proof-based questions? I don't know. But anyways, you're not supposed to do all of them. Your instructor picks a few based on probably what you covered in class. But the idea is that in an introductory course, it's easier to disprove something. There are some things that can be proven or disproven in mathematics. So I don't want to make a blanket statement and say like disproving things is easy, because it's a little naive. It's easy in your first classes because why? Because you only have to find a counterexample. And here, if my statement was to prove or disprove the converse of our original statement, then it would be pretty simple to disprove this, because we just have to find a pair of supplemental angles that are not a linear pair, which we have done here. Okay, so now we've looked at the converse. Let's look at the inverse. Okay, so remember, now, hold on, let me just erase this so I don't get rid of I'll just do like this. So according to our truth table, when I write down this converse, did I say converse? When I write down this inverse, I should actually have the logical equivalent of the one I just wrote down, which was the converse, right? Okay, so the inverse is not P implies, oops, when I read it, tilde, not P implies not Q. Okay, so what can we do with this? Well, first of all, what does it mean? It means we would have to write it like this. So if two angles are not a linear pair, oops. So if two angles are not a linear pair, then they are they are not supplementary. Okay, so we know this is false. How do we know it's false? Because of the example we just did, we found two angles that are supplementary but are not a linear pair. So this one is not true. Okay, now let's go to the contrapositive, which should be the logical equivalent of the original conditional statement. So our contrapositive is going to be not Q implies not P. So since this is logically equivalent to the first conditional statement, it should be true. So not Q implies not P. This means that if two angles are not a linear pair, wait, what? I'm doing backwards. Hold on. Thinking about something else. Should focus on this. Okay. If two angles are not supplementary, okay, there we go. then they are not a linear pair. Okay, so this is definitely 100% true. And proving it, now, how do you even prove that? Well, in this case, proving it would be a little, I don't know, it's sort of an axiom. I mean, can we prove that to be true? Probably. I've got another example for proving it. But this is definitely true, because if it's because it's part of the definition of a linear pair that they are adjacent to each other on a line. And so they have no choice but for their sum to be 180 degrees. Okay, that's just basically it's the inbuilt into it's an axiom of a linear pair. It's impossible for them to not add up to 180 degrees. Okay, so if you have two angles that are not 180 degrees, if not 100, not, hold on. If you have two angles whose sum is not 180 degrees, it would be impossible for them to be a linear pair by definition. Okay, so let me just talk about, now we do have more complicated statements that we can create out of conditional statements and out of binary operators. And typically that's how you'll see things presented in mathematics. You'll see that the P is actually, you know, a combination of statements put together with the binary operator, usually an and. If this and this are present, then we are guaranteed to have this conclusion, some proposition might say. And so that's usually how you will go about, usually how you will see things is that you'll get something like this. Actually, I don't want to deal with that one. You'll get something where you have more than one condition to start with. Okay, so an example might be like here I've got Pythagoras theorem. And this is an example where actually the converse is true. But it says if ABC is a right triangle. So, and actually here you may think, well, a right triangle, there are actually two conditions. The first condition is that it's a triangle. And then the second one is that it's a right triangle. And then we can reach some conclusion. All right. So what I mean is that typically you're going to have things such as this statement here. If P implies Q and Q implies R, then P implies R. So this is similar to what we call property of transitivity. And so typically, yeah, you'll have statements like this where, let's see, it looks like I started this and didn't finish it. You'll have statements like this where you are connecting them with the logical operator to create the hypothesis, if you will. Okay. All right, so the next thing I want to do is give you an example of when you might use the contrapositive, and then after that, if there's time, I've got to give you some ideas about some notation. But first, let me give you an example of using the contrapositive of a statement to prove something, because a lot of times you'll often see it's difficult to prove a statement the way it's written, but if you can rearrange it into the contrapositive, then it's a little easier to prove the contrapositive. So using contrapositive to prove. Okay, and so here's my theorem, my proposition, if you will. My theorem is this: if n squared is an even integer, then n is even. Okay, so this one is a little difficult to prove because if you start, well, first of all, if you start with the forward, if you start in the forward direction using the P then Q, you're going to run into some problems. And let me show you what that might be. So first of all, it says that n squared is even. So before I start to prove it, let me just write down a few things. And what does that mean? Well, remember that any even number can be divided by 2, and it's an integer, okay? So one of the key properties about integers is that they are closed, we call closed under addition, they're closed under multiplication, meaning that if I add 2 integers together, I will always get an integer. If I multiply 2 integers, I will always get an integer, and I can't get a decimal or a fraction, okay? So if n squared is even, then n squared is equal to 2 times some other integer m, because that's the definition of an even number, is that I can divide by 2. Okay, so those are multiples of 2 that can divide by 2. And here, this can represent any multiple of 2, provided that m is an integer and varies throughout all the integers. So we would say where m is an integer like this. Okay, so while I'm doing this, I'll introduce some additional notation. This means, well, maybe not, because I'll just do that at the end. So m is also an integer. Is an integer. So if n squared is even, then it would be of this form. Okay. All right. Now, what we want to do is we want to prove, or we want to show, this is how we write it, that n is equal to 2k for k, also integer. Okay, so typically, how might you try to do this? Well, it would be pretty normal, natural to just try to take the square root, but then you end up with something like this, which is like, well, what do you do from here? Okay, so it may be a little difficult to prove it in this direction. I'm not saying it's impossible, but I'm saying in this case, there's something easier we can do, and that is to use the contrapositive. So what would the contrapositive be? It's not Q implies not P, right? So in this case, what does not Q imply not P mean? Well, it would mean that, so Q is, n is even, right? So not Q would mean n is not even. What does that mean? It means that if n is not even, then n is odd. Those are the only 2 possibilities. You might say, what about 0? Isn't 0 even? I think it is. You might want to check. So if n is not even, then n is odd. What does odd mean? Well, odd numbers are after the even numbers, if you will. So if I take an even number 4, what's after that? An odd number. If I take an even number 6, what's after that? An odd number. So how do I go from even to an odd? I have to add 1. So that means that n is, well, first of all, n is odd if it's not even. And that means that n is equal to 2. So an even number plus 1. So 2m plus 1. And then m is an integer, of course. We're only dealing with integers. Okay, so this would represent any odd number that we can try to calculate that's an integer. Okay, now that's what not Q means. So if n is even is Q, so not Q means that n equals this odd number. Okay, so now we're ready to start the proof. We want to show that if n is not even, then not P, then n squared is not even. So in other words, then n squared is also odd. So let's go ahead and do the proof now that we have the basic ideas. And this is just like a little taste of what's to come, really. Okay, so Finished erasing. Okay, so let's do the proof of the contrapositive. So we'll write proof, and we'll say by way of contrapositive. You don't need to write that, but it doesn't hurt. And there's a whole style to writing proofs, and you basically, there's some guidelines, but you can kind of find your own way. Okay. So proof by way of contrapositive. So we'll say, let n be equal to 2m plus 1 for some m integer. And we'll say, we'll just say n is an integer before we start. Okay, so n is an integer. Let n equal 2m plus 1 for some m integer. So what am I saying here? I'm saying that n is not even. So I'm saying not q. That's what I've said now, not q. Okay, so n is an odd number. Then we'll say take n squared. And what do we get when we square n? We have to take this side over here, also square it. So take n squared equal to 2m plus 1 squared, which means 2m plus 1 squared is the same as 2m plus 1 times itself. And now we expand this however you like. I use FOIL out of habit. So 2m times 2m, I get 4m squared plus 2m times 1 plus 2m plus 2m times 1 again, and then plus 1. So, okay, so here we go. Does this look like an odd number? It should, but there's something we have to do to make it more convincing. So we need to take out a 2 here. And then we've got 2m squared plus, so if I add this together, I get 4m, take out a 2, I have 2m. So I've got 2m like this, plus 1. Okay, now, now I didn't factor out all the 2's, and the reason is because I want it to look like a odd number. So let me just say this. So let's say k equal 2m squared plus 2m, an integer. So definitely k is an integer if I substitute k instead of this expression, right? 2m squared is 2 times 2 other integers plus 2 times another integer. So we said earlier, multiplication of integers times integers produces integers, and adding integers also produces integers. So here we definitely get an integer. So we get that n squared is equal to 2k plus 1, which is definitely an odd number, an odd number. And that's what we wanted to prove. So we proved what? We proved that if n is an odd number, then when we square it, we get another odd number. So if n is odd, n squared is odd, which is the contrapositive to what? Well, let's write down the contrapositive, which proves, it proves what? It proves that if n squared is not odd, meaning if n squared is even, then n is not odd, meaning that then n is also even. And that's what we wanted to prove. Okay, so before I end the video, I do want to write down some symbols that we're going to be using. Okay, and to do that, well, first I'll start with numbers, number sets. Actually, okay, I guess I got to start with sets, don't I? Okay, so a set, there's a definition. And so basically what I'm going to do is called naive set theory introduction. Why is it called naive? Because it's actually much more complicated than this. And actually, one of the most, what is it? There's some predicate logic ideas where you start with something, but you don't know what it is. And yeah, I don't want to go down that rabbit hole. So anyways, let's start with the definition. A set is we'll say well-defined collection of objects. Okay, so well-defined means we know if something is in the set or not, and collection of objects means that, well, actually it could be empty. So the collection of objects could be no objects, the collection of no objects could be a set. But the typical sets that you will see are numbers. So like the natural numbers. The natural numbers are numbers that, for the purposes of our class here, we use this symbol n, and they're defined to be, so this symbol right here, I'm writing, it looks like an equal sign, but it has two dots in front, okay? So this means it's defined to be, we're going to say 0, 1, 2, 3, up to infinity. Okay, so we're taking 0 to be a natural number because we'll use, later on, we're going to use something called Peano's axioms to construct the natural numbers. Right now we won't, though. And then the next example will be the integers. So the integers are what we call, well, okay, you'll come to know what this means, but if you take all of the natural numbers and their additive inverses, meaning that there's a number we can add to together with another number that gives us the identity. So all of this meaning that the integers are the natural numbers and their inverses. The additive identity is the number that when you add something to it, you get nothing, you get the same thing back. So 0. And so there's a lot of really interesting properties and structure to these number sets that we'll talk about if I can stay on track here. So the integers are going to be written like this, from -3, -2, -1 to 0, 1, 2, 3, and then we just continue on to infinity. And we will construct the natural numbers from the integers. The next set of numbers we'll deal with are called the rational numbers. And the rational numbers, I guess I should write down the name first. The rational numbers are constructed from the integers, and we will go through that construction. Oops, I don't want to write it down like that. Try that again. So the rational numbers are numbers that can be represented as a ratio. If a number cannot be represented as a ratio, then we consider it. And when I say represented, I should be more precise. I mean precisely represented, okay? Because every number you could represent as a ratio if you only approximate it. But when we talk about rational numbers, we're talking about only those numbers which the fraction precisely represents that number, okay? So a rational number, we call it Q, and it's defined to be like this. So it's let me write it like this. We'll say it's A divided by, actually I want to use, I usually use like P and Q. Yeah, I like P and Q. We'll say it's a P divided by Q such that P and Q are both integers and Q is not 0. Okay, so there's our definition of the rational numbers. Okay, then we have the irrational numbers, and I can't really write down. Okay, so I have to do like this. In order to define the irrational numbers, I first have to have something called the real numbers. Okay, so the real numbers are, I'm going to define it like this. Okay, they're equal to Oh, I can't because I don't know. Oh, I have to talk more about sets first. Okay, so before I can do this, I have to define some other things. Okay, so these are your examples of sets. Okay, we've got sets of numbers. Now, let me talk about the objects. The objects I mentioned in a set are called elements. And we can write down some notation like this. So we'll say let A be a set if Q is an element of A, we write Q is in A like this. And so we can say is an element of, belongs to, any of those will work. And it's sort of like a small e. So I'll give you an example of another thing we can do. I could write down 1/2 is an element of the rational numbers. But 1/2 is not an element of the integers. So it's not an integer, but it is a rational number. Okay. Now, what about sets? Can a set be in another set? Yes, in fact, we can say that. So here's another definition. We'll say that B is a subset of A if, now I can write it like this, for every B in B, that same B is in A. Okay, so for every B in B, that same B is in A. And now that gives rise to another bit of notation I want to use here. Okay, this word for every, we can write using like an upside down A. And so it could also be for all, for every, like that. So, and then the notation for a subset, we write like this. So B is a subset of A. If and only if, let's write down if and only if for all B in B, that same B is in A. Okay, and so these two, you see we've got a biconditional statement here. Now there's such a thing as a proper subset and an improper subset. And honestly, I don't usually use that much, but so I have to remember which one is which. But that means that one of them can be equal to the set and one of them cannot be equal to the set. So let me just remind myself, what am I talking about? Proper subset. Hold on a second. Improper. Okay, yeah. So yeah, typically, I mean, I've been doing math for a while, hardly ever use it, right? Except when I'm teaching it. This is basically it. Okay, so I don't use proper and improper very often. It does come up though. So this would be considered a proper subset if I write it like this, proper. But it could also be like this, meaning that, and by the way, this also could be, we also use the word contain, and I could write it like this as well. I could write it like this. So this saying B is a subset of A, this saying A contains B. Okay, so, but you also have the situation where it's possible that B could be equal to A. And in fact, that's a whole nother definition called set equality. So this would be improper subset if it's possible for B to also be equal to A. So definition, so we'll say let A and B be sets. A is equal to B. And this also is going to tell us, you know, how can we prove two sets are equal, which we might often have to do. A is equal to B if and only if. So I would write it like this: for all B in B, B is in A, and for all A in A, that same A is in B. So in other words, that means that B is a subset of A, and A is a subset of B. Okay, so that's the case that they're equal. If the two sets are a subset of each other, then they must be equal. Okay, and that's how you go about proving that two sets are equal. And I forgot to say, oh yeah, so this is A is equal to B. So A is equal to B if and only if B is a subset of A and A is a subset of B. And that's what we call set equality. Okay, so what am I doing here? So we're talking about sets now. We talked about some examples of sets and the elements in the set. I introduced the idea of a subset, which is important, and then the difference between proper and improper, and then we come to set equality. Okay, so the last thing I want to do is, and I'll talk more about this, is talk about set operations. And we have operations called, we use this symbol here, this is called the union. We have this symbol here called the intersection, because this is what's going to allow me to talk about the real numbers. And then we have also, for sets, we have complement. And so let's see, if A is a set, then A complement looks like this. I'm going to use this symbol, but actually there's so many of them. There's this one, there's this one. Okay, there's just too many, but I like the A with the C on top. Okay, so if A is a set, we'll say let A equal, and I'll just give you like a really down and dirty example here. B equal 0, 2, and 3. Okay. So an example of the union, we would write A union B is equal to the set that includes everything that's in A and everything that's in B. Okay, now remember when we talk about propositional logic, this is similar to and. This is similar to that binary operator and. So this is a way we can combine the sets. Okay, then we have intersection, which should remind you of or. So A intersected with B, or A and B, is only the elements that are both in A and B. So in this case, it's just 2. It's the only one they have in common. And then we have not A. And when it comes to complement for sets, usually we say, well, we've got two ways of writing this. We've got A complement, and then we also have the complement of A with respect to B. So I would write it like this: complement of A with respect to B. Okay, so for me to talk about not A in this context doesn't really make sense, because we don't know, like, is A a part of another set of numbers? So let's just say, just to give you an example of complement, then we'll say like A is a subset of some set C, and C is equal to 1, 2, 3, 4. Okay, so then not A would be 3 and 4. So when it comes to set theory, we will use this not A more generally, but a lot of times it's within the context of another set. So if I want to talk about A complement of B, so I'm sorry, the complement of A with respect to B, that's going to be everything that's in A but not in B. So it's a little different than what we said. So everything that's in A that's not in B is just 1. Okay, so let's see. Where else do I want to go? I'm just gonna, I feel like maybe I said something wrong, so I'm gonna check it. I'm fine. Okay. So not A, just, everything that's not in A. So if A, I guess we see this a lot if we have intervals. So let me give an example of this. Most of you probably already understand the real number line. So here's the real number line. Okay. So suppose I define A to be the set here, where this number is like 3 and this number is 5. So suppose I said A is equal to the open interval from 3 to 5, right? So then not A would be from negative infinity to 3 and including 3 in union with 5 to positive infinity. Okay, so that's how we would talk about not A, like this. This is an example. Okay. Or, and I'll do this more later, we can talk about it in terms of a Venn diagram, which will be useful for probability. So suppose here I've got two sets, A and B. And so then not A complement would be everything that's, not A. So it would be all of this. And that would be our not A. Okay. And there are corresponding graphs that we can draw for each of these. And I think I'll do that next time. So let's see if I got to where I want to go. I want to be able to talk about what are the real numbers. And I think I can do it now. Okay. So what are the real numbers? Well, first of all, note, and then I'll stop the video, I think. Note that the natural numbers are a subset of the integers, a proper subset of the integers, right? And then the integers are a proper subset of the rational numbers. By the way, some people also write it like this. That also means it can't be equal, right? So up to you. And then inside of the natural numbers are a subset of the integers. The integers we can construct the rational numbers from the integers. The integers are a subset of the rational numbers. And then we have all of these are contained in the real numbers, but there's another set here. Because obviously, there are more real numbers than just natural numbers, integers, and rational numbers. There's a whole, and actually these are probably more of these numbers than there are of the very nice ones. And the numbers that go here are called irrational numbers. And these are numbers that cannot be precisely represented by a ratio. Okay, so some people use this symbol, a bold I. But the symbols, the symbols really came from a time when typesetting was difficult, I guess. So a bold I could be the irrational numbers, but most people don't write it like that, I think. So examples of irrational numbers are going to be pi, the square root of any prime number. And the reason is because these numbers do not terminate and they do not repeat. So it's impossible for us to convert that decimal into a fraction. Okay, so the best we can do is approximation. I have to really grow out of this pet peeve that people not use this to be pi. This is not pi. It's a very gross approximation, but I got over it being pedantic. But at any rate, pi cannot be written down. These are numbers that cannot be written down. Certainly, I've written it like this with this symbol. But if you were to try to write pi, you would die before you finished. And in fact, all of humanity, as far as we know, would die because it cannot be written. Okay, so it's irrational. And what are the irrational numbers? Well, we can use this symbol I, but usually people write it like this. It's the real numbers without the rational numbers, like this. Okay, so this is how we define irrational numbers. The real numbers without the rational numbers. And so that takes care of the integers and the natural numbers too, because the rational numbers contain the natural numbers and the integers. Okay, and so then we can define the real numbers to be the union of all of these numbers. Well, actually, maybe I shouldn't write it like that. Well, probably not. Let me just try to write it down like this. It's the union of these two sets of Q and not Q. Is that right? Maybe. I think it sounds right to me. Okay. It should be, yes, because the rational numbers include integers, natural numbers, and themselves. And then this set includes everything that's not in here. So put those together and we should have the real numbers. The only thing I worry about is we're not including, well, you can't include infinity and they're not numbers. So, okay. We have one more number set, which is like the big kahuna of the number sets, which is the complex numbers. So the complex numbers have as a subset the real numbers. So complex numbers are numbers, and I won't go into it now, I guess, a plus bi. A plus bi, where the a is a real number. Well, okay, actually, I can write it like this. So the complex numbers C is defined to be these numbers a plus bi, such that a and b are real numbers, and I is equal to the square root of -1. Okay, so in the real numbers, we don't have negative square roots. But the complex numbers, we can extend this idea of a solution to this equation. And by defining the solution to this equation as the number I, we actually get an entire new set of numbers that contains the real numbers. And so actually the real numbers are a subset of the complex numbers, which means that every other number set also is a subset of the complex numbers. And yeah, and these number sets have various properties. The real numbers and the complex numbers, these are fields. And we'll talk more about what a field is. The real numbers are a complete ordered field. The complex numbers are an unordered field. And then we have our rational numbers, which are also what's called a field. And we'll talk more about the underlying structure of these numbers. But the integers and the natural numbers are not a field because they do not have the structure required. So we're going to talk about this idea of the structure of number systems. And so let me, and also more about propositional logic and proving. But let me go through some more notation first. So for all, or for every, looks like this, upside down A, there exists, we often say that, there exists is going to be a backwards E. There exists a unique one. I'll write it like that. Looks like this. And let's see, what else do I want to use? such that, I might write down like this. So I'll just give you an example, and then I'm probably going to stop the video. I'll say for all m in Z, there exists an n in Z such that m plus n equals 0. Okay, so that would be how we might use these symbols. And actually, I could even modify this into a theorem that we have to prove, which would be for all m in Z, there exists a unique n in Z such that m plus n equals 0. So now I'm saying, there's only one n that when I add it to m in all of the integers, that gives me 0. And this actually is true, and we can prove it later on. Okay, so I think that's it for today's class. Thanks for watching. If you have any comments or questions, please post it. If you notice a mistake, please let me know. Thank you, and have a great rest of your day.